So
So
I can,
all right, so hold on. Are you able to record? Yeah,
I am able to record. Thank you.
All right, perfect. Yeah, so go ahead, Tammy.
Welcome to our first seminar of the season or semester. Thank you so much for joining us. Dr. Liang here to speak about batteries beyond batteries. And I'm going to let Liang go ahead and give a little bit of history on himself so that you know who he is and what his history is.
yeah. So hi everyone. So I'm Liang He. I'm a faculty assistant professor in the Department of Computer Science. My research is on cyber physical systems and Internet of Things, and I named my lab here in CU Denver as CPS Laboratory. Yeah. So I have been working at, let's say, I joined CU Denver in 2017, and so my research. Most of my research originates from batteries and also goes beyond batteries. So that's why I titled this talk as Batteries Beyond Batteries. And the intention is to use it to cover to most of my recent research and ongoing research as well. Yeah. So shall I get started?
Yeah. Yes, thank you.
Thank you.
Just please, thank you. Yeah.
And Dr. Lee, hey, do you mind if we take questions during the
Sure, anytime.
Okay, so if anyone wants to put any questions into chat, we'll go ahead and or raise your hand or something. We'll try and get that attention. Otherwise, we'll go ahead and have time for questions at the end as well.
Yeah. So as I mentioned, this talk I will try to cover most of the recent and current ongoing research in my lab. So here I listed the three major topics I will cover in this talk. The first one, we start with battery management. And second one, we call it battery sensors and actuators. And the last one, and the most recent one, is something we call cross-domain system invariants. These three topics or three concepts are actually originating from batteries and goes beyond it, and they are evolving, as you will see. And the research covers different typical cyber physical system platforms, including mobile phones, mobile tablet, and vehicle systems defined in the broad sense, and also manufacturing systems. So let's start our talk with this battery management. So battery management is actually a very typical cyber physical problem, because whenever we're talking about battery management, we have the physical space, we have the device, we have the battery, we have the environment. And then we need some kind of algorithm in terms of communication, computation, and control to run the task of battery management. And more importantly, this battery management task must be designed based on the unique battery properties and also executed with some kind of algorithms in the cyberspace and achieving the ultimate goal of improved system operation. An additional challenge talking about the battery management is in most of the cases, we are talking about user-centric application. That said, yes, our objective is to improve battery performance, but we cannot do that at the cost of degraded user experience. So in the next, I will use one example of battery property, what we call the relaxation effect, to show you how we can use this relaxation effect, a physical property of battery, to improve the battery management. And by definition, relaxation effect, we mean it just let the battery rest whenever possible. And when we are saying let the battery rest, we mean reduce or terminating its discharge or charging current. So letting the battery rest offers multiple opportunities to improve battery performance. And let's see particularly how it can help us to solve the problem of unexpected phone shutoff. Okay, so by definition, again here, the unexpected shutoff means the phone shutoff when it's showing larger than 0 remaining power. And if you are a user of iPhone, then very likely you will heard of this free battery replacement program from Apple in 2016. And the reason why it is because for a particular batches of iPhone 6s, this phone suffers a lot of unexpected shutoffs. And from Apple, the reasoning is to say these batteries degrade faster than a normal battery and cause unexpected shutoff. So what does it mean? For a given battery, normally we capture it with at least 2 different metrics. The first one is something we call design capacity. That's the number usually marked at the outside external of the battery. And it means then the capability of the battery to store the power when brandly new in the ideal case. But in practice, we know batteries got weaker and weaker over time. So we have another concept called full charge capacity. That's to say the battery right now, after fully charged, how much power it can contain and supply. And there will be a mismatch between this design capacity and the full charge capacity. That's the red part, what we call inactive. That also represents the aging of the battery. And we know this battery basics now, and let's see what does degrade faster than normal mean. Degrade, of course, is very clear. It means the red part, that's the inactive part, and this inactive part will increase over time and usage. And faster than normal, that means that the increase of the red part is really fast than expected. And more particularly, it means it increased very fast, so the iPhone cannot really accurately capture it. And if that's the case, it will cause overestimated full charge capacity. In our example here, assuming this is the ground truth, right now showing on the left, and with this overestimated over full charge capacity, the iPhone 6s will think something like this. That means, hey, there's an extra portion of remaining capacity that's actually not there. And this will cause the overestimation of SOC as well, and causes eventually the unexpected shutoffs. So now we know the reasoning behind this issue. We can translate this sentence from Apple to another one more technically. So that means actually it's the error in full charge capacity estimation caused unexpected shutdowns. And when we're talking about battery management, there is a metric called state of health. It's essentially a normalized metric to describe a full charge capacity. So by replacing it, we can simplify the sentence again by saying error in SOH estimation actually causes unexpected shutoffs. So SOH estimation is one of the most well-studied problems talking about battery science. But still, even Apple suffered from this inaccurate estimation. The reason why is, yes, we do have a lot of excellent algorithms to estimate SOH, but we need to think about whether those algorithms can be deployed on phones. A particular example is many of these existing SOH estimation algorithm requires a battery property called impedance as the input. But to collect that particular battery property, we need a very, let's say, particular device that costs over 5K itself. That said, yes, we do have algorithms, we do have solutions, but those solutions very likely only works in laboratory. Putting them onto phones where we don't have a lot of information of battery, that is really challenging. And actually, even nowadays on phones, the most, let's say, the only pervasively available information is actually the battery voltage. So the question is, can we doing some kind of battery SOH estimation just using voltage? And our answer is yes, we can. We can use relaxation voltage to fingerprint battery SOH. Let's use this measurement to show the feasibility. So we used a battery for Samsung phone. We fully charged the battery. After fully charged, we rested for 30 minutes. That's relaxation, let the battery rest. And then we fully discharge the battery. So that means during this fully discharge, we can collect the full charge capacity, and so we can calculate the battery SOH. We repeat this cycle for 300 times. And this is the result. During the first cycle, when we are resting the battery, we have this voltage curve. And also after the discharging, we calculate, and then we find, hey, at this first cycle, the battery SOH is about 90%. And this is the curve for the 300th cycle, the last one. We have a similar curve, but lower. And also we have a similar number, but also smaller. That's about 86% of SOH. So by looking into this measurement, we can see there is a potential mapping between the voltage curve and the number of battery SOH. And if we can capture this kind of mapping, we can do a SOH estimation based on the relaxing voltages. Actually, this mapping can be explained using a circuit model of batteries, which I will not detail here for this in this talk. So based on this observation, we have designed a solution to estimate the battery SOH based on only voltage. We have tested on phones over 4 months, showing a less than 5% of estimation error. Even though you are not using iPhone 6s, okay, you may still suffering from unexpected phone shutoffs, especially if you are using it outside in the winter time. And so let's check what's happening. So we started this thing with environment. We got a Xperia Z from Sony. We fully charge it. We put it into operation in a cold environment. So you can see the phone shut off after about 660 minutes. Okay, and then it shut off when the voltage, when the SOC is still something about 20%. And what we do is we after the phone shut off, we move it back to the room to warm it up without charging. And then we try to turn it on, and it turns on and it operates for another 18 minutes. So why this thing happen? So let's again go back to the mobile phone. Here I showed a very simplified circuit model of mobile device. On the left side, we have a model, we have a circuit for the battery. On the right side, we have a simplified logistics for the device. So in order to power the phone, to keep the phone on, we need a voltage from the battery that is larger than a cutoff level. Okay, so on our phones, normally that's 3.3 volt. And if we further simplify, let's further simplify the circuit model. We combine the resistance, the capacitors as the overall resistance, we call it R. And then what we need is a voltage from the battery that is satisfying this kind of relationship, where this IB here is the discharge current of the mobile device. And if this is the case, we will be able to see very clearly both this IB and the internal resistance of the battery are dynamic. As a result, when we are using the phone, especially in cold temperature, there is a chance the phone will shut off unexpectedly. And what makes it even worse is two things. We use it in cold temperature, so we have a larger R here. Or we are using the phone, let's say, intensively. That means we have a larger IB here. Both of these things increase the voltage drop and make it more likely to happen for the unexpected shutoffs. What Apple did about this? Yes, Apple has a solution, and that's updated in the iOS 10.2.1. And what Apple did is just trying to slow down the processor when the SOC of the battery is low. And as a result, if we check the performance, overall performance, computation power of the phone, we can see after this update, the phone got slower. So as an end user, we can well expect people will not be happy about it. And actually, this update caused multiple lawsuits against Apple, and eventually it's a $500 million settlement. And our solution, we call it BPM, Battery Aware Power Management, to address this unexpected shutoffs in code. In general, this solution, this is a middleware for iPhones, for mobile devices, and in general, it consists of two parts. The first part is during charging, we apply relaxation or duty cycle charging to capture the resistance of the battery. That's the R in the previous equation. And then at runtime of the device, we want to schedule and regulating the discharge current of the battery. So that means we regulate the IB here. And then by combining these two, we can mitigate the unexpected shutoffs and extend the phone operation. Yes.
Dr. He?
Yeah.
We do have our first question.
Sure.
Are there similar unexpected shutoffs in hot weather above 100 degrees Fahrenheit summer day, for example, like in the cold weather?
Yes, there are issues with that, different issues, but also starting from batteries. Okay, because if we operating batteries in hot temperature, we are not worried about whether there are enough juice inside the battery. We are worrying about whether the battery will become too hot and then got on fire. So in short, yes, we have a similar issue but different. Okay, and that's also the reason why if let's say you are driving your car in the summer, put your car using your car as navigation, put it in the front, right? So that means the sun is always hitting the phone, and after maybe 30 minutes and 1 hour, your phone will be shut off, and you will receive an alert message to say, hey, the battery is just too hot, we need to shut it off. Yes, there are issues, okay, but different issues. Yeah. So we have this BPM design, and this BPM is actually published at a conference we call it ACM Mobicis. And it's one of the top tier conference in computer science. And something I want to mention is our shepherd in that conference. For the shepherd is the one who determines whether this paper will be eventually accepted or not. Is actually a domain expert from Apple. Let's go back to this Apple's problem, 500 million cost again. There is another keyword we didn't cover. That's the old. Okay, it means we may suffer magnified risk of unexpected shutoffs when we're talking about aged batteries. Batteries age, battery got weaker over time and over usage. That's the nature, we can do nothing to stop it. But how fast the battery age actually is determined a lot by how we use it. And here a particular focus is we find the onboard charging solution of phones is well designed, believe me, it's well designed by Samsung, by Apple, by many other companies. But they are not very good for to keep the battery, to slow down battery aging because they are short of user awareness. So let's start it by checking about what's existing solution on board of mobile devices. In general, we call it two-phase charging, called constant voltage, constant current and constant voltage charging. So what does it mean? It means whenever we are charging a battery, or maybe the mobile device battery, we have two phases. The first phase is what we call it is a constant current. That means we use a large current to charge the battery. And because we are doing this, both the voltage and the SOC of the battery will increase faster. And once the voltage increase reaches a maximum level defined, the charging process switches to a second phase, what we call it constant voltage phase. And in that phase, we control the charging voltage and make it constant. And as a result, the charging current will gradually reduce. And once it reduces it to a very small level, for example, 100 milliamps on many phones, we say, hey, the phone is fully charged. And so you can see, as a summary, the existing onboard solution charges phones in two phases. The first one is constant current charge and then constant voltage charge. And this charging phase is determined by three different configuration variables. These variables are written in the charging driver. And then if we summarize this part again to say we will see this is the offline plant charging process because all the three numbers are written in the driver, they're constant. Whenever we are charging, we follow the charging process defined by the three numbers here. Second one, the charging goes with first faster and then slower. Then the question is, CV charge, the second phase is slow. Why do we bother to have it? Why don't we just go with CC charge to make it even faster? The reason is CV charge slows down battery aging. So there is a good reason why we incorporate CV charge into this charging process. Okay, here I listed the three observations here, and let's check how this well-designed battery charging method is used in practice. What we did is we collected about, oh, okay, go ahead.
Somebody asked, does fast charge affect on the battery lifetime?
Yes, that's the dominating factor.
Thank you.
So we collected about 1,000 charging cases from 7 users. So we just monitor the charging period. And then more importantly, here we showed the end of charge SOC. That to say, when you are disconnecting your charger, what's the SOC showing on the phone? And from this about 1,000 cases, we can see about 40% of the charge terminated before the battery is fully charged. So that's how we use the phone in practice. And then if we combine this design of charging method and how we use it in practice, we can see we will have very often we will have prematurely terminated battery charging, and we know the last part of the charging is CV charge. That means in practice, we may very likely have incomplete or even totally skipped CV charge. And we know CV charge slows down battery aging. So if we don't use it, somehow we are accelerating battery aging. To address this, we designed another charging method. We call it RAW, or relaxation-aware charging. In general, the objective is, first, again, we want to charge as much as possible, but we want to ensure enough relaxation to keep the battery at a good health state for a longer time. And also, this charging must be finished within the limited charging time. The basic idea is, previously for CCCV charge, we have one of the control parameter called Vmax. And right now, in our design, we split it into two variables. We call it VCC and VCV. By using these two variables, we can make the CV charge phase start earlier and make it shorter. So we have tested this RAW on mobile phones again, and the results showing about 30% slowdown of battery aging on average. And also then it comes to a question to say, what if I really need fast charge, right? So what we design is another, let's say, a GUI, a user interface of phone charging. That's to say, whenever we are charging the phone, this GUI will pop up, and then based on our real-time needs, the user can determine or maybe configure how to charge the phone. If you really need fast charge, go with onboard fast charge. If you don't need it, so you can afford a little bit of slow charging, you can use our solution to charge it slower, but we can keep the battery healthier for a longer time. A final word on this design is, very clearly, we are talking about the two variables, VCC and VCV. And talking about the algorithm design, we need to kind of identify some sense of optimal combination of these two variables. And if you're talking about this problem, in a very high level, we are talking about a two-dimensional search for these two variables. And then by applying a couple of physical properties of batteries and also the charging process, we can reduce this searching space from a 2D space to a 1D. And also we can safely apply a greedy search to identify the optimal. That means low computational complexity. So we talked about the 3 different projects we have done on battery management. And right now, if you're using iPhone, you can go to your iPhone and check the battery health and the charging module on your iPhone. You will see 3 different functions offered by Apple. Actually, the 3 projects we just talked about covers each of them. And actually, we have more. We have the designs on SOC estimation in code and also the charging in code. Yeah, Tammy, go ahead.
Sorry, pushed the wrong button. Is that why charging Apple devices at the 80% mark overnight, the charging will slow and then the charge will finish around 5 a.m. the next day because the current is lowered?
The first part is true. That's the reason why that's the case. But they want to control that part. But let's say it's not only because the current is lower. Yes, it is true the current is lower, but if that's the only reason, without any further control, still we don't really need to wait until 5 in the morning. Okay, for example, the charge can be finished at 1 p.m. We don't need that kind of long time. The reason why we want to do that is we don't want to keep the battery fully charged for a long time. That's also bad for battery. Yeah.
Then they said if from using iPhone, if you choose battery save mode, it will charge faster. Is that correct?
I don't think these 2 parts are actually technically related.
Okay.
Battery safe mode is more on the discharging management part. It, for example, slow down the processor. It can dim the display. It can disable some kind of modules to save power, to reduce the power consumption. It does not really handle the charging part of the battery.
Thank you.
Yeah, thanks for the question. So that's the battery management. And let's revisit battery management. What do we have talked? We have a battery, we have a phone, we want to make the battery better. To do that, we need to monitor the battery constantly. So we need to collect voltage, temperature, and current. That means we need to collect data. And then based on this raw data, we can have algorithms to estimate some further battery properties such as SOC and SOH. Okay, we need to collect data based on the data and to optimize battery performance. But battery data is also closely related to how we use the phone, or maybe how the system is operating. That said, there is a dependency between system operation and battery power. And if we already know the battery power, the battery data, there is a way, or maybe there's a possibility for us to say something about the system operation. It's a reverse direction. So that said, this concept is what we call batteries as sensors and actuators. As a first try, because we have talked about a lot on mobile phones, let's still use mobile phone as example. We have mobile phones, we need to monitor the phone battery all the time. And we know very intuitively, there is a dependency, there is a correlation between battery temperature and the ambient temperature of the phone. And if we were able to decouple this kind of coupling between the two temperature, we should be able to make the phone battery a thermometer. Actually, that's our first project, the first exploration in this concept called battery as sensors. And of course, it's not easy, okay, because the battery temperature is determined by a lot of other factors, including user behavior and also some other, let's say, phone modules. So eventually, this exploration is successful. It's published at another top-tier conference in computer science called UBCom, and people like it. And this paper is invited, a short version of this paper is invited to ACM Get Mobile. Okay, the first try is successful, and supported by that, we extend our exploration further, and we change the platform now. We change it to cars. And now the observation, or maybe the basic of that, this research is something we call, the conjecture is the 12-volt battery of cars can be used as a physical channel to monitor and control car operation. We have done in general, we have done solve the two problems in this direction. One is on vehicle immobilizer and the other on vehicle anomaly detection. Let's start with vehicle immobilizer. Like it or not, we are suffering increased auto theft. Okay, I list some numbers here. 2019, we suffered over $6 billion from auto theft. 2020, we have 9% increase. 2021, we have even more significant increase of auto theft. What makes it even worse for us is Colorado, and specifically Denver, is becoming one of the worst places in terms of auto theft. A key reason contributing to this auto theft is we use cars to immobilize we use keys to immobilize our cars, but right now keys are no longer a safe solution because they are vulnerable. They have been shown vulnerable to a lot of different attacks, and this vulnerability actually covers cars for most of the manufacturers. And actually, recently, in last year's Black Hat conference, there are researchers from Singapore reporting they can hack the car to steal hack the key to steal the car without even doing the replay attack. Okay, so it's really kind of ironic. Okay, we use car keys to protect our cars, but actually those keys are actually being hacked more and more often to steal the cars. Batteries offers a solution to mitigate these cyber vulnerabilities. This is based on two observations. The first one is very clear. If the battery do not supply enough power, no one can start the car. And the second one is the car is connected to the driver cabin or passenger cabin. And so there is 12-volt power line network connecting the battery to the driver. And we can use this 12-volt power line network as a medium to achieve driver authentication. So that means observation one, we can use battery as actuators to control vehicle driving. Observation two, we can use batteries as sensors to allow the drivers to authenticate him or herself to the battery. By doing this, we can use batteries to design a new vehicle immobilizer that is physically isolated from common cyber attack vectors. That is the external accessibility and also in-vehicle network. This is the overall picture. I know it's complex because it is an end-to-end system. We are working on the fourth version of the prototype of this vehicle immobilizer. So in general, this immobilizer consists of two parts. The front end, that's a dangle plugged into the car that interact with the driver, accept the driver input of authentication information and deliver that information to the backend. That's a module installed onto the car battery. And the backend will authenticate the driver based on the received information and disable or enable the driving based on the authentication results. And if we're talking about functionalities, the whole system we call BVIM consists of 4 different modules. The first one is driver authentication. The second one is access control or power control to dis or enable driving. The third part is a set of alarms to detect an abnormal behavior. Okay, someone is trying to steal my car. I want to trigger an alarm. And the last part is the power supply. Yes, Tammy, go ahead, please.
Are older vehicles with key fobs and other security devices just as vulnerable, or is it just more newer vehicles with better computers that are vulnerable?
Everything wireless is vulnerable. Everything used in vehicle network is vulnerable. Yeah, so yes.
Thank you.
Yeah. And when we are designing this thing, our results actually, let's say resulted in 2 or 3 research papers. The first 2 are already published, and the third one is under revision. And this BVIM will win the Lab Venture Challenge in Colorado last year, in 2021. So let's talk about this the 2 authentication methods we used. The first one we call it is behavior-based driver authentication. The key idea is actually quite straightforward. Okay, when we are triggering some kind of electrical operation of the car, we are triggering a unique voltage pattern of the battery. For example, when we are swipe the wiper, when we are rolling the window down and up, you can see the voltage pattern is actually quite unique. And this kind of unique voltage pattern can be used as a signal to authenticate the driver. And by doing this, what we can do is, as a driver, you can define your password to start a car as a operation. For example, you can define your authentication operation as a swipe the wiper twice. And then whenever you want to start your car, you need to do this authentication operation. And at the back end, we will monitor the battery voltage and then match that battery voltage with this operation to see if they agree. If they agree, you are the good guy and the engine cranking is enabled and you can start the car. That's the basic idea. And this challenge actually is a lot because the battery voltage varies with a lot of different context factors, such as the background operation of the car. Or let's say some operations is very difficult for the human being to repeat operations exactly the same. And also the voltage is also determined by battery temperature, state of charge, and age. So we need to solve these issues in order to deliver this solution. The second solution we proposed on top of it is a quicker and more convenient solution. It's an encrypted power line communication system. So it's kind of a full stack communication system, including a circuit layer at the bottom, modulation layer at the middle, and application layer at the bottom. And designing this end-to-end communication system requires us to solve a set of design challenges, including determining what's the better signal carrier. Shall we use voltage or current? Talking about the signal modulation, we need to determine the frequency and the magnitude. Talking about the communication, we need to talk about the symbol duration, and we want to add a layer of security. So that means we need to handle encryption. And also another thing is we need in most of the cases talking about to save the cost of the system, a asynchronous communication system is more straightforward. But asynchronous communication incurs additional design challenge. And the last one is, yes, we are talking about a system that we needed from time to time, we don't know. So the system needs to be keep active for most of the time. We need power saving. So that's what we call the sleep and active state transition. We have tested this battery-enabled vehicle immobilizer on 8 different cars with, let's say, additional of 3 different batteries at different age states. And the performance shows over at worst case performance of 99.9% of accuracy. And also we have corroborated the user acceptance, the usability using both survey and user studies. In total, we have checked the opinion of users from over 800 participants of what do you think about this BV. There is a demo video on YouTube you can check if you're interested. Last word about this thing is talking about vehicle immobilization. We provide a solution called BVM. And actually BVM is a solution that potentially replaces car keys. And if we can do that, this will be really good for 2 purposes. The first one, vehicle immobilization, because we are talking about a new solution that is secure and we don't need to carry anything. The second one is this solution to be really, really good for fleet management. Because for fleet management, the keys is always the bottleneck. We need to handle the pickup, the return, the maintenance of the keys. It's kind of a troublemaker for fleet managers. Another one direction, what we call it vehicle anomaly detection. Again, this crashes of airplanes, I believe many of you have noticed. And what's the reason here? What the root cause of these crashes is wrong sensor readings cause the wrong control decisions and eventually caused crashes of the airplanes. The abnormal sensor readings is kind of a common problem for all engineering systems, including vehicles and airplanes. And in this Bible, it's kind of Bible textbook talking about automotives. They refer this a concept called cross-validation, or maybe in their terminology, they call it model-based sensor failure detection. They view it as a promising approach to detecting anomalies. Okay, so the idea is to evaluate a particular sensor by model-based calculation from other sensors. And then they also, in this Bible, they also mentioned a set of key challenges. Do we need to deploy additional sensors to do the cross-validation? And if yes, how many? Do we need to change the car design, retrofit it or not? And also, we're talking about cross-validation between 2 sensors. If something goes wrong, which sensor to blame or which sensor to trust? So we find batteries can actually serve as a solution to all of these questions, because batteries operate in strong dependency with many vehicle modules, and the battery voltage can be easily collected without going through the in-vehicle network, making them trustworthy. An example is shown here. Okay, when we are driving a car, we have the engine. When we are driving, the engine will rotate and then cause a rotation of the alternator. Alternator will generate power, and this part of this power will be used to charge the battery. So if this is the case, in a simplified version, we can see if the engine RPM is larger, that means the engine is rotated faster, we should be able to observe a higher battery voltage. This kind of physical dependency determined by how the car is designed, and using this kind of dependency, we can do the cross-validation. And actually, we can do beyond the battery engine RPM. So right now, based on our results, we identified 22 different vehicle variables that can be diagnosed using battery voltage. And then another challenge in here, talking about this kind of battery-enabled diagnostic, is how do we know which sensor we can cover? So to solve this question, we developed a graph model to abstract the car as a 2-layer graph model, and also together with an automated data-driven approach to determine which sensor can be diagnosed using battery information. Again, we tested this solution on cars, and the solution is quite promising, over 86% detection rate, which to me is very good, talking about a data-driven solution. And also, because we have this generalized graph model and also the method to generate this graph, we can apply this thing to other systems. For example, we have applied the solution, extended the solution to drones, and currently we are supported by NASA. We are applying this idea to satellites. we talked two different problems. And if we put these things in more a security terminology, we can see talking about vehicle immobilizer, we are talking about driver authentication and access control. And talking about intrusion detection, we are talking about anomaly detection. Essentially, we are talking about intrusion detection. So combine these two parts, actually, we can provide a comprehensive battery-enabled cybersecurity management system, which is very important because right now the cars is frequently hacked by attackers, and this also inspires us to rethink the physical security. For example, we can use battery as a last layer security solution. Yeah, Tammy, go ahead.
Does adding more sensors affect on the battery? Does adding more sensor affect on the battery?
The sensor itself, no. Yeah, because sensor, we are not talking about a small battery. We are talking about 12-volt battery that's relatively strong. And talking about the sensors, the power consumption will usually be really, really negligible compared to the power of the battery. Yeah. So that's the thing, how we, starting from battery management, we extended it to batteries as sensors, a new research concept. And we apply that concept to first mobile devices and then cars. Let's do a further extension. When we are talking about the batteries as sensors and actuators, for example, when we are talking about these batteries as thermometers, essentially we are exploiting the dependency between the power consumption of the mobile device and the surrounding environment. And when we are talking about the cars, essentially we are talking about the power consumption or generation of the battery, the operations of the car, and also the SCADA data, the monitoring data of the car. So all those things, there's some kind of dependency. Those dependencies are defined or maybe, let's say, generated because how the car is designed. We call this cross-domain system environments. For example, environments across the environment domain and power domain for the mobile phones, environments across the power operation and the data domain for the cars. And we want to generate it further and apply it to manufacturing. Why manufacturing? Manufacturing is one of the most targeted industry talking about cybersecurity. Okay, and I will be brief about this part. This let's say, very simplified high-level figure shows the scenario of a manufacturing system operation. In general, as a human operator, we use some kind of development software to download a operation code to the industry robot. And this downloading, definitely we are talking about some kinds of communication. It's done through the industrial network. So a manufacturing device, or maybe, for example, industry robot here, after receiving this code, it will operate following the code as defined by the code. And then the SCADA, if you report the operation data, or maybe for the robot, it's movement data to the SCADA. And the SCADA will apply some kind of anomaly detection algorithms to say whether this device is operating as expected, and also report that data back to the human operator. This is in general how this manufacturing system is let's say, operated. And actually this applies to all automated systems. And then let's talk about vulnerability. We're talking about communication. So industrial network has been known to be hackable. So if that is hackable, attackers can potentially hack through the industrial network and change the operation code. So the result is the robot will operate, let's say, in the malicious way. We have designed a attack, proposed an attack, and validated attack actually in this problem, to say we can not only manipulate operation of the manufacturing device, but we can also let's say targeted manipulating. It's not random. We can target it. We can specifically determine how we define the malicious operation of the robot or the manufacturing device. And as a solution, we also have a IDS, intrusion detection system, that is based on the invariance between the system control and the system operation that can detect this semantic attack. And then we have a more advanced stealthy attack that can void this IDS we just mentioned. And the idea of this one is, yes, that idea, the previous ideas you mentioned, you are built on this invariant between control and operation. And this attack will just avoid this control and operation invariance without being detected. And then as a solution, we have a new manufacturing system, a manufacturing paradigm designed to detect this stealthy attack using the invariance between code and operation data. So we know the operation code can be hacked, but even the SCADA data is reported through this industrial network. So really powerful attackers can jointly manipulate both the code and the data. And that what we call is a deception attack. I can manipulate the operation. On the other side, I can correspondingly modify the monitoring data. Okay, in this way, the SCADA or the human operator will not be able to detect the manipulation. And then as a solution, we use the invariance between the system power consumption and the system operation to develop an IDS to detect these deception attacks. So for this part is relatively the new. I just briefly mentioned this. Let's say 6 different projects we have been through. As a quick summary, so I talked about 3 different research themes that's happening in my group. We are doing here in our department: battery management, battery sensor and actuators with a particular focus on cars, and the cross-domain invariants with a focus on manufacturing. And let's say future research, or maybe let's say the future plan for each of them, we do have things. Battery reuse, talking about battery management, we need to handle battery reuse and recycling, because electric vehicle is not only featuring anymore. We have very commonly seen electric vehicle now, but after 5 years, these EVs the batteries will going worse, and then we need to think about how to recycle and reuse them. Talking about the battery as sensors, our plan is to apply this thing to further advance the smart transportation. The uniqueness here is our position is we are not trying to develop smart cars based on this concept. Instead, our focus is how to make the traditional dummy cars a little bit smarter in order to help us to achieve the smart transportation. And the last one, talking about manufacturing, right now, one of our focus is to have a real application of trustworthy biomanufacturing that's achieved by all of our current results. Yes, so that's everything. Thank you for your time. And our research is, let's say, supported by different agencies, including both federals, industry, and of course, U Denver. Thank you.
Does anyone have any questions?
I have several questions about the battery management system.
Sure.
I'm from mechanical engineering, so I'm not an expert in a battery or like EE stuff, but I still having a question about first about the SOH. As a SOH, the definition is the maximum capacity of the battery divided by the rated capacity, right? And yeah. You mentioned the device to measure the SOH gonna cost like 5K, but I'm wondering, with basically the capacity of the battery, the actual capacity of the battery can be measured by monitoring the current, the time, and also voltage of the battery, right? So I thought in this case, the device to measure the SOH shouldn't cost that much. Is that correct?
Yes. If the algorithm only use current or voltage, we don't really need a 5K device. The 5K device is to collect impedance. That's another battery property. It's not so easy to collect it. But the advantage of if we have that information, the SOH can be monitored and estimated with even higher accuracy. Yes, what you mentioned is definitely correct. So our issue here is we have the solution, but we want to deploy the solution on phones. And on phones, what do we have, right? On phones, even nowadays, so even we're talking about nowadays high-end phones, we have 3 different things: voltage, current, and temperature. That's all we have. Okay, and even current, if we don't focus on high-end phones, current may not be available either. So that's that. Talking about existing mobile devices, the only pervasively available information of battery is the voltage. And that triggers up the question, can we design a solution that is based on only voltage so we can ensure deployability?
Okay, got it. And second question is for lithium-ion battery, it's well known that it's gonna do self-discharge. And the early days, I used to fly model aircrafts, and the self-discharge is a big issue for the battery when we store it. And at that time, usually the charger, they have a storage mode, like they maintain they charge the battery to about like 80%, and then we can store it for a long time. And my question is like for nowadays, does the battery management system have any algorithm? Let's say we left the phone at 90 or 100% of voltage of the battery and leave it alone, or maybe lower like 40, 30% of the battery. Will the battery management system do any measure to protect the battery?
This is a good question and a big question. We can answer it from multiple aspects. Okay, there's no easy answer. Let me try to give you several cases. Assuming you are talking about storage, you're not talking about I have this battery, I put it into phone and use it. If you're talking about I have a lot of battery, I don't need it, I need to put there in a warehouse. If that's the case, yes, it's true. We in the industry, let's say, recommend to charge it in somewhere in the middle, 60%. Okay, and so for storage purpose. And if that's the case, the self-discharge may not be a really issue here. The main purpose for that thing is to try to not fully charge it and keep it fully charged for a long time, because that's really bad for battery health. Okay, talking about that thing. On the other side, if you're talking about self-discharging on some kind of application, for example, mobile devices, actually that's related to the question we had. Let's say we charge the battery and wait until, let's say, 5 in the morning to fully charge it. So what's happening in phones is for example, we only need 2 hours to fully charge it, even with the CV charge, which is slow. Okay, but after that, okay, after fully charged, it's 100%. And if we do not disconnect the charger, and definitely there will be self-discharge. Okay, and then you will see 100 after some time it reduces to 99%, right? And if this is the case, for example, we charge it overnight. At 1 a.m., it's fully charged 100%. And then when the user wake up in the morning, he or she may see, hey, my phone is 98%. Something wrong with my charger. Doesn't make sense, right? That would be an issue. And to address this issue, let's go back to our question, does mobile phone have some solution to handle this? Yes, they have. What they call it is a tickle charging. To say after, at 1 a.m., after the phone is 100%, it will stop charging, that's true. But after some time, it will keep charging, start charging again. But of course, with a very small power. And it only charge it to 100% again and stop it. And then after time, 100 becomes 99 again, it charges again. They call it tickle charging. This is a solutions particularly designed to handle this self-discharging.
Usually, nowadays, if we buy a battery pack to replace, for example, like a Bluetooth receiver or something, which have a lithium battery pack, I noticed that it always comes with a battery management circuit board there. So, does that mean this kind of algorithm is being integrated into most of this kind of battery?
Yes. So yes, let's say first thing, yes. And on top of it, I need to explain a little bit more about this. So battery management right now, whenever we're using it, it's really already a very small integrated chip. In most of the batteries, talking about, for example, if you get a new battery for iPhone or for any mobile device, the chip is already embedded inside the battery. We cannot see it. Okay, there is a chip inside. So that's true. And also talking about battery management, it's just, let's say, how much we manage. in the most, let's say, entry level, when we're saying battery management, we are saying there is SOC estimation. That's to say 19% power, 80% power remain. That whenever the battery, the smart battery provides that function, we can say this is a smart battery, and this has some kind of role of battery management. But of course, battery management is not only about SOC estimation. We also have SOH estimation. We also have temperature control, and even many others. Balance, talking about large-scale battery packs. Okay, temperature balance, SOC balance, SOH balance. Yeah, so it's kind of, yes, in general, what I can answer you is unless what you got is some kind of naked battery cell, there are already, very often, there are already some kind of chips, battery management chips buried inside the battery. But how many advanced function it provides, it really depends on the application, or maybe, let's say, particularly which kind of chips you got.
Okay, and my last question is,
Chen, can you hear me?
Yeah.
So I'm happy that you're asking a lot of questions, but in the spirit, if allowing other students to participate, let's see
sorry.
if other students have more questions, and then we can come back to you, okay? Is that good? So any questions from other students at all? Okay, so Giselle is asking a question here, and she wrote it. So she said, how does low power mode work, and how does it affect battery age?
I think this is related to the question Tammy raised during the talk. Yeah, so low power mode, we are focusing on, very often, we are focusing on reducing the power consumption of the device. It may not directly handling battery management. Okay, talking about the battery age, of course, if we are reduce the discharge rate, definitely it's good for battery aging. Okay, slow down the battery aging. But anyway, the main purpose of power save mode is not to slow down battery aging, but to save power, make the system operate longer.
Very good. So there is another question from another student, I believe, which I will read for you, Liang. It says, for a typical car operating system, what coding language do they typically use? And does that coding language usually operate the integrated circuit in the car? Also, when people still hack cars, is it a direct link to the car computer where they have to have access to the inside of the car? So it's like two questions.
Okay, the first question, talking about, I think the first question is it means you are interested in talking about, let's say, coding, implementing something to hack it. And I got excited about this. Yes, my experience, C++. Okay, so inside cars, we have a lot of microcontrollers. Normally we call it ECU, electric computer control unit. You can view it as just an embedded controller or maybe small computer inside the car. And inside the car, we have a large number of those things. And all those different functions are implemented on these microcontrollers, and how my experience about implementation, those things is using C++, but I cannot say this is the only solution. Okay, that's for the first question. For the second question, do we need a direct link to this microcontroller? Yes, we need a link, of course. So normally for this hacking, if we're talking about, I assuming, let's say, because we are already talking about the microcontroller inside the car, we are talking about in-vehicle part. We are not talking about wireless communication, hacking the car from outside. Okay, so normally the internal hacking of the car happens through the OBD2 part. OBD2 part is kind of mandatory part that are available on all cars after I think 1996. Okay, and that's a part where we can access all this. We can potentially access all those microcontrollers inside the car, and the thing connected the part with these microcontrollers is something we call a bus line network. And very often that's a CAN network. Okay, so yes, there is a link, there is a network already deployed. And also because of this, we have this linkage, we have this access to the microcontrollers. There is a risk we can hack them. Okay, so if if you Google it, search it on YouTube, you can find a video to say how hackers can plug a malicious dongle to the OBD2 port and disable your car alarm.
Very good. So there's another question here. So you focus on Apple phones. Do the same concepts apply for all smartphones brands, or do they use different kinds of batteries?
Yes, it applies to all kinds of phones. Actually, majority of our experiments or our implementation experiences on Android phone for a very clear reason, because Android is open. Okay, development on iOS, we can do that, but the flexibility is quite limited.
Okay, so I have a question for you also, Liang, if I may. So, I come from, a power perspective on this topic. And one thing that, is kind of like difficult for us is to establish an accurate model for the batteries. So in one slide, you showed a model, with resistances and one capacitor, I believe. So I don't know if you have followed, the evolution of the battery models, or perhaps, that you look at this problem, more from a computer science or cyber physical approach. I mean, what kind of models do you use? Are those critical for you to do your analysis and whatnot? I mean, if you could, talk about battery models in general a little bit.
So the battery model I showed in the slide is a circuit. It's one of the most simplified model.
Correct.
The reason why we use it because that's the information we can collect on phones. If we're really talking about high precision, high accuracy battery model, it goes beyond the control. Okay, a lot of talking about circuits, talking about the control, the configuration variables. We have a huge of them. Okay, so that's you see, you have talking about the science. We really need those excellent, very highly accurate models to capture better performance. Nothing wrong with it, and a lot of people are working on that. And from computer science point of view, I myself is not a battery material guy. My focus is to have some kind of algorithm, right? We can use and we can improve the battery performance. We need to think about, we have good model, can we deploy it? And to do that, definitely we need to sacrifice something. We need to simplify it. And that's why we came to this circuit model. It's one of the most simplified model already.
Okay, very good. So I don't know if anyone else wants to ask a question by talking. Any questions from the audience at all?
Sorry, one last question.
Yes, you can. So I was gonna actually give you the opportunity to ask your last questions. Yes, please. Go ahead.
Thank you. So I used to disassemble some the battery pack of some power tools, and I noticed that they were using a lithium ion phosphate battery. And I found out like most power tools, they use this kind of battery. And it seems that it's very robust and like does not need as much care as other other lithium ion battery. So my question is, does this kind of battery also require some kind of battery management system, or we can treat it as a traditional nickel hydride battery, which is carefree?
Okay, so my bad. When I'm talking about battery management on phones, I assume we are talking about the lithium-ion batteries. Okay, so actually all the work is based on the results or maybe the observation on lithium-ion batteries. On the other side, what you mentioned is definitely true. Lithium-ion batteries right now is very popular. It's the dominating types of batteries for a reason, because it's definitely be better than the previous generation of batteries in some sense. One particular case, for example, what we call it the memory effect. Okay, in previous 20 years ago, when I talking about some types of battery, we know if the battery is new, we always want to fully charge it for a couple of cycles in order to fully activate it. Otherwise, part of the battery will become inactive and stay inactive for the lifetime. Lithium-ion battery do not have such kind of big issue, talking about memory effect. Okay, so definitely yes. But on the other side, is lithium-ion battery the perfect solution already? Do we have, let's say, do we have need or space to further improve it? Definitely yes, we can always improve. Nothing is perfect. Okay, we know Samsung Galaxy 7 got on fire. The battery got on fire in 2017, right? And if you check, actually, it's not only on phones. Check about the Boeing airplane, again, in around 2010, there are lithium-ion battery on the airplane got on fire and caused the whole fleet to ground. Okay, and also, yes, one actually compared to previous batteries, a advantage is lithium-ion batteries talking about the cycle life is better. Okay, we can survive, for example, a random number, for example, 2,000 cycles, discharging cycles. And then people agree, 2,000 are good or not. It's better than previous, but are they the best we can get? If we can have a new generation or maybe a way to improve this 2,000 cycle to 3,000 cycle, do you want it or not? Right? So you can see there's no ending. Lithium-ion battery is better than before, but we can still improve it, and we need to improve it. What we are doing is improve it from management point of view. Okay, algorithm design and control. And there are battery guys talking about, for example, solid state battery. That potentially right now, that's the most popular concept we are talking about in battery materials. Okay, if that thing ever happens, it's kind of magnitude improve of, let's say, performance when compared to lithium-ion batteries.
Sorry, my question is a lithium-ion phosphate battery like other lithium-ion battery require BSM system, or it does not?
Yes.
I mean, comparing to other lithium-ion battery, lithium-ion phosphate is more like robust, more kind of carefree, because in the battery pack of power tools, they usually the model I disassembled, there's no like BSM chips or circuits there. So that's why I'm wondering if they are more carefree or they still like other lithium-ion battery needs BMS.
My answer is yes. But on the other side, to answer your question is, we also need to think about, do we need it? We can always use carefully designed battery management to improve battery performance. But in practice, do people really need it? Talking about the phones, because we use it all the time, we don't want a phone to let's say, the battery to be too weak after 1 year, right? So definitely battery management is important here. Talking about the Tesla, we are talking about the safety issues. We are talking about very expensive battery packs. Yes, we need to do the battery management. But talking about the power tools, we need to think about it. Do we really need very carefully designed power management or not? Everything there is a dollar there. Okay, you implement algorithm, you implement module. That's good, improve the performance, but it requires more money. $1 is money. Do this $1 actually, let's say, help the manufacturing make $2? Okay, that to me, I feel my first idea is that for some applications, maybe they don't really need it.
Okay, thank you very much.
Okay.
Very good.
It's not the type of battery, more like application.
Okay, thank you, Liang. So any other questions from the audience before we wrap up here? Well, if not, I would like to first thank Dr. Liang He for an excellent seminar. And I would like to remind the students that the next seminar is on February 7th, 2 weeks from today. And I also made available on Canvas, or I created an assignment on Canvas for you guys in case you want to submit your one-pager on this seminar, okay? So anything else? If not, as I said, thank you everyone for attending, and thank you, Liang, and I will see you guys in 2 weeks from today. Thank you so much, and bye.